Before you close your eyes tonight, I want you to think about something. Right now, as you breathe, as the world outside goes quiet, as the light fades and the darkness settles in around you, there is a planet out there, a real planet, a world, something enormous, 5 times the mass of Earth, wrapped in ice and frozen gas, drifting through the absolute cold of deep space. And we have never seen it. Not once, not a photograph, not a telescope image. The way you know something is in a room before you see it. We know it the way you know something is in a room before you open the door, the way you feel a presence in the dark before your eyes adjust. Not because you can see it, because everything around it is behaving as if it is there. The planets at the edge of our solar system are moving in ways they should not be moving. Their orbits are tilted and stretched and clustered in patterns that should be statistically impossible, patterns that have a less than 1 in 500 chance of occurring by random chance. Something is causing those patterns, something massive, something distant, something we have not yet found. And as you drift towards sleep tonight, we are going to go looking for it, all the way to the edge of the solar system, into the darkness beyond Neptune, then into a region of space so remote that sunlight takes hours to reach it, and so cold that the temperature hovers 200 degrees below anything you have ever experienced, into the place where Planet 9 is hiding. Welcome to Science for Sleep, the place where the universe slows down. Tonight's journey begins with a question that has been haunting astronomers for over a decade, a question so simple it sounds almost childish. How many planets are in our solar system? You probably answered 8. Most people answer 8. Since 2006, when the International Astronomical Union redefined what counts as a planet and demoted Pluto to the status of dwarf planet, the official answer has been 8. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. 8 planets, 1 star, a solar system we have been studying for 400 years, mapped and measured and modelled in extraordinary detail, a solar system we thought we understood. But here is what the data is starting to suggest to us. We missed one. The solar system we thought we knew. Let us begin where all good journeys begin. At the beginning. 4.5 billion years ago, there was no solar system. There was a cloud. An enormous, slowly rotating cloud of gas and dust, hydrogen and helium and trace amounts of heavier elements forged in the hearts of stars that had lived and died long before our sun was born. Something disturbed that cloud. Or perhaps the shockwave from a nearby supernova, a dying star's final explosion rippling outward through the galaxy and compressing the gas cloud just enough to start a collapse. Perhaps the gravitational influence of a passing star. Perhaps simply the slow accumulation of mass at the cloud's centre over millions of years until gravity could no longer be resisted. Whatever the cause, the cloud began to contract. As it contracted, yet it spun faster, the same physics that makes a spinning skater speed up when she pulls her arms in. The spinning cloud flattened into a disk. At the centre, the temperature and pressure rose to extraordinary levels. The hydrogen at the core began to fuse. A star was born, our sun. Around the newborn sun, the remaining disk of gas and dust began to cool and clump. Dust particles stuck together. Small clumps became larger ones. Larger ones swept up more material as they orbited. And over millions of years, the process continued, aggregation, collision, growth, until distinct bodies emerged. In the inner solar system, where temperatures were high and the lightest gases had been blown away by the young sun's radiation, rocky planets formed: Mercury, Venus, Earth, Mars. In the outer solar system, beyond what astronomers call the frost line, the distance from the sun at which temperatures are cold enough for water ice to form, a different kind of planet emerged. Here, icy and rocky cores grew large enough to capture the abundant hydrogen and helium gas that surrounded them. They became giants: Jupiter, Saturn, Uranus, Neptune, and beyond Neptune, in the cold outer reaches of the solar system, the process of planet formation stopped. Or rather, it slowed to the point of incompletion. The material was too spread out. The orbital periods were too long. Collisions were too infrequent. Instead of one large planet forming in this outer region, the thousands of smaller objects remained, a vast ring of icy bodies that astronomers call the Kuiper Belt. For most of the 20th century, this was the picture. The solar system ended at Neptune. Beyond Neptune was the Kuiper Belt. Beyond the Kuiper Belt was essentially nothing. the vast, cold, empty interstellar space between our solar system and the nearest stars. A neat picture, an orderly picture, a picture that turned out to be incomplete. The Neptune is 30 times farther from the Sun than Earth is. At that distance, the Sun is not the brilliant disk of light we see from Earth. It is a very bright star, brighter than anything else in the sky, bright enough to cast faint shadows, but a star nonetheless. Not a sun, not a warmth-giving, life-sustaining presence. Just a very bright point of light in an otherwise dark sky. The temperature at Neptune's distance from the Sun is around -200 degrees Celsius. Beyond Neptune, it gets colder. The Kuiper Belt extends from roughly 30 to 50 times Earth's distance from the Sun. It contains hundreds of thousands of objects, icy bodies ranging in size from small rocks to dwarf planets like Pluto, Eris, Makemake, and Haumea. It is a crowded place by the standards of the outer solar system, though by any human standard it is almost unimaginably empty. Beyond the Kuiper Belt, the density of objects drops sharply. There is a region called the scattered disk, a sparse population of objects with highly elongated orbits that carry them from the inner Kuiper Belt out to vast distances, and beyond that, theory predicts, is the Oort cloud, a vast spherical shell of icy objects extending perhaps a third of the way to the nearest star, the source of the long-period comets that occasionally fall inward toward the Sun. Nobody has directly detected the Oort cloud. It is too distant, yet its objects too small and too cold to observe with current technology. It is inferred from the behavior of comets, from the mathematics of orbital mechanics, from computer simulations of the early solar system. It is, in other words, known the same way Planet 9 is known, not by seeing, by inference, by the footprints left in the behavior of other things. This is how astronomy works at the edge of the solar system. You cannot always see the thing itself. But if you look carefully enough at what surrounds it, at what it influences, at the subtle gravitational whispers it leaves in the orbits of smaller objects, you can know it is there. And in the mid-2000s, a series of discoveries in the outer solar system began leaving exactly those kinds of whispers. The first was a small reddish world discovered in November of 2003 by an astronomer at the California Institute of Technology. His name was Mike Brown. And what he found that November would set in motion a chain of events that 20 years later may be about to reveal a hidden planet at the edge of our solar system, the object that started everything. Sedna. It was named after the Inuit goddess of the sea, an appropriate name for an object discovered in the cold outer reaches of the solar system, a world of ice and silence at the very edge of everything we knew. When Mike Brown and his colleagues calculated Sedna's orbit, something immediately struck them as wrong. Sedna's closest approach to the Sun, its perihelion, was at roughly 76 times Earth's distance from the Sun. That put it well beyond the Kuiper Belt, and at its most distant point, its aphelion, Sedna was nearly 900 times Earth's distance from the Sun. The orbit was enormous, bizarre, unlike anything else that had been catalogued in the solar system. But what truly puzzled Brown was the perihelion, 76 astronomical units. The Neptune, the planet whose gravity shapes and defines the Kuiper Belt, orbits at 30 astronomical units. Every object in the Kuiper Belt has an orbit that at some point brings it relatively close to Neptune. Neptune's gravity is the dominant force in that region. It pushes things, pulls things, shapes orbits. Sedna's perihelion at 76 astronomical units was too far for Neptune to have placed it there. Neptune's gravity simply does not reach that far with enough strength to have sculpted an orbit like Sedna's. And so what put Sedna there? Brown published the discovery and the puzzle. He noted that Sedna's orbit was inexplicable under current models of the solar system. He suggested several possible explanations: a distant stellar flyby in the early solar system perhaps, or the gravitational influence of other stars in the young sun's birth cluster. He did not suggest a planet, not yet, but the question stayed with him, and over the next decade, as more objects like Sedna began to appear, objects with orbits that defied easy explanation, objects clustered in ways that seemed to point toward a common gravitational influence, the question grew louder. What is out there? Something is shaping these orbits. Something massive, something distant, something we have not yet seen. The hunt for Planet 9 had begun. There is a name that every astronomy enthusiast knows, a name that, depending on who you ask, that is either celebrated or mildly resented. Mike Brown, the man who killed Pluto. That is not strictly speaking accurate. Brown did not personally demote Pluto from planetary status. The International Astronomical Union did that, in a vote that Brown himself has described as somewhat chaotic and not entirely satisfying from a scientific standpoint. But it was Brown's discoveries in the Kuiper Belt, discoveries that revealed Pluto was not a unique world, but merely the largest known member of a vast population of icy bodies beyond Neptune, that made Pluto's demotion scientifically inevitable. And Brown knew it. He had known it for years before the vote. He had said so publicly in papers and interviews, with a directness that some found refreshing and others found needlessly provocative. Pluto is not a planet, Brown had argued. But not because it is small, size alone does not determine planethood, but because it had not gravitationally dominated its orbital neighbourhood, had not cleared the region around its orbit of other debris, the way the 8 true planets had. Pluto was one of thousands of similar objects in the Kuiper Belt. Calling it a planet while not calling Eris, discovered by Brown himself in 2005, and initially found to be slightly larger than Pluto, a planet was scientifically inconsistent. The IAU agreed in their contentious 2006 vote in Prague. Pluto became a dwarf planet. Brown became famous or notorious, depending on your attachment to the 9-planet solar system of your childhood. But the story of how Brown came to make the discoveries that changed the solar system's membership, and how those discoveries ultimately led him toward the evidence for Planet 9, begins not with Pluto or Eris, but with a quieter, stranger world. It begins with Sedna. The discovery of Sedna, November 14th, 2003. Brown was at the Palomar Observatory in California, reviewing images taken by the 48-inch Samuel Oschin telescope, a wide-field survey instrument that Brown and his colleagues had been using to systematically search for large objects in the outer solar system. The images were taken automatically. The telescope scanned the sky in a predetermined pattern, taking multiple exposures of each field separated by hours or days. The software then compared the images, looking for objects that had moved, that had shifted position against the background stars in the time between exposures. On November 14, 2003, the software flagged an object that had moved. Brown looked at it. It was faint, fainter than most of what they had found before, but it was there, clearly moving against the background stars, clearly a real solar system object. He calculated a preliminary orbit from the available observations, and stopped. The orbit was unlike anything he had seen. The object's closest approach to the Sun was at roughly 75 astronomical units, far beyond the outer edge of the Kuiper Belt. Its most distant point was somewhere around 900 astronomical units, nearly 30 times farther from the Sun than Neptune. Brown named it Sedna, after the Inuit sea goddess. The name felt right for a cold, distant, reddish world at the edge of everything known. And when he published the discovery and the puzzle of Sedna's orbit, an orbit that no known planetary influence could explain, he opened a door that 20 years later may lead to the discovery of an entirely new planet. Why Sedna matters. To understand why Sedna's orbit was so puzzling, you need to understand the architecture of the outer solar system and the role Neptune plays in it. Neptune is the gravitational gatekeeper of the outer solar system. At 30 astronomical units, this is the outermost of the giant planets, and its gravity dominates the region from roughly 30 to 50 astronomical units, the Kuiper Belt. Objects in the Kuiper Belt have orbits that at some point bring them close enough to Neptune for its gravity to have influenced them. Sedna's perihelion at 76 astronomical units was squarely in this beyond Neptune territory. Neptune's gravity could not have placed Sedna there. It is too far. And if a passing star or the Sun's birth cluster had scattered objects into highly elongated orbits, those objects should be scattered randomly. Their orbits should point in all different directions. There should be no preferred direction, no clustering. When 2012 VP113 was discovered in 2012, its orbit had properties similar to Sedna's. And when astronomers looked at the orientations of both orbits, they found that Sedna and 2012 VP113 were not pointing randomly, that they were pointing in similar directions. Two objects was not enough to be statistically compelling. Two objects could be a coincidence, but it was enough to be interesting. Enough to make careful scientists take note and watch for more. More came. By 2014, there were 6 known extreme trans-Neptunian objects with orbital properties similar to Sedna's, and all 6 had orbits pointing in roughly the same direction. so the probability of that clustering occurring by chance was approximately 1 in 1,000. Something was shepherding these objects, guiding their orbits, leaving its gravitational fingerprints on everything at the edge of the solar system. Brown picked up the phone and called Konstantin Batygin. The rest, as they say, is history in the making. Sedna has a technical classification in the literature of planetary science. It is called a detached object. The name is evocative. Detached. Not cut off. Separated from the gravitational influence that shapes everything else in the outer solar system. Objects in the Kuiper belt are, in a sense, connected to the rest of the solar system through Neptune. Neptune's gravity touches them, shapes them, scatters some of them into new orbits and stabilizes others. There is a thread of gravitational influence running from Neptune outward through the Kuiper belt, linking even the most distant Kuiper belt objects to the planetary architecture of the inner solar system. Sedna is not connected to that thread. Its perihelion is too distant. Neptune cannot reach it. It orbits in isolation, following its vast elongated path around the Sun without any known planetary body to guide it or perturb it. This is what makes it strange. How did it get there? What put it in that orbit? What maintains it there? And these questions have no satisfying answer in the standard model of the solar system. Something is missing from the picture. When astronomers discovered 2012 VP113, nicknamed Batygin, they found a second detached object, same general region of the solar system, similar orbital properties, merely the impossibility of explanation under the standard model, and the directions their orbits pointed were similar, not identical, but similar enough to suggest a common influence. The statistical case. Let us talk about numbers for a moment. When Brown and Batygin published their 2016 paper, they based their analysis on 6 extreme trans-Neptunian objects. 6 is a small number. Critics were right to point out that small samples are unreliable, that patterns in small datasets often disappear when more data is collected. But the dataset has grown. By 2021, the number of known extreme trans-Neptunian objects relevant to the Planet 9 hypothesis had grown to more than 30. By 2024, it was approaching 50. Each new discovery has been an opportunity for the clustering signal to disappear, for the new objects to point in random directions and dilute the pattern. The clustering has not disappeared. In 2024, a team of researchers published a comprehensive analysis of 51 extreme trans-Neptunian objects. To their conclusion, the clustering is real. The probability of it occurring by chance, accounting for observational selection effects as carefully as they could, was approximately 1 in 500. 1 in 500. This is not proof. Science does not work by probability alone. A 1 in 500 chance event can happen. It happens all the time when you are dealing with large numbers of possibilities. Statistics can mislead. Selection effects can create spurious patterns. The skeptics continue to raise these concerns, and they are right to do so. Scientific skepticism is not obstruction. It is how bad ideas get filtered out. But the signal keeps surviving the scrutiny. The Ammonite. In early 2025, astronomers announced the discovery of a new Sedna-like object. Designated 2023 KQ-14 and nicknamed the Ammonite. After the spiral-shelled prehistoric creatures, it had a perihelion of approximately 70 astronomical units and an enormous, highly elongated orbit. And its orbital properties put it squarely in the category of detached objects inexplicable by the Neptune's influence. And its orbit, when plotted, aligned with the cluster of similar orbits already known. The Ammonite was not a surprise to the Planet 9 theorists. It was a prediction. Before the discovery was announced, the Planet 9 hypothesis predicted that more Sedna-like objects should exist in roughly the orbital orientations that the known objects defined. Whether the Ammonite fit the prediction. This is how scientific hypotheses are tested. Not just by finding supporting evidence, but by making specific predictions and checking whether those predictions come true. The perpendicular orbits, one of the most striking predictions made by the Planet 9 hypothesis, and subsequently confirmed, involves objects in highly inclined orbits. Most solar system objects orbit in roughly the same plane, the ecliptic. But when Brown and Batygin ran their computer simulations of the outer solar system with Planet 9 included, they found a surprising prediction. Planet 9's gravity should pump some extreme trans-Neptunian objects into orbits that are nearly perpendicular to the ecliptic. Objects with inclinations of 90 degrees or more. At the time of the prediction, no such objects were known. They were subsequently discovered. and several objects with inclinations between 90 and 140 degrees have been found since 2016. They were not predicted by any other model, they were predicted by Planet 9. Make a specific testable claim, have it confirmed by subsequent observation. The planet's fingerprints are everywhere at the edge of the solar system. We just need to find the planet itself. Konstantin Batygin was not supposed to believe in Planet 9. He has said this himself, and in interviews and lectures and the kind of frank scientific retrospectives that researchers give when a long project finally reaches a turning point. He was not a believer. He was a calculator. He looked at the data Brown showed him, and his first instinct was to find the flaw, to identify the selection effect or the statistical artifact or the measurement error that would make the clustering go away. He could not find the flaw. But this isn't important to understand about how the Planet 9 hypothesis developed. It was not born from enthusiasm or wishful thinking, or the desire to restore a 9-planet solar system. It was born from a skeptic failing to disprove it. Batygin is a theorist. His work is mathematical, the kind of planetary dynamics that involves differential equations and phase space and the long-term behavior of gravitational systems. And he thinks in orbital mechanics the way a musician thinks in notes, not as symbols on a page, but as a living, intuitive language. When Brown brought him the clustering problem, Batygin initially approached it as a puzzle to be dissolved. Show me why this is not real. Show me the alternative explanation. Convince me that there is nothing here. The alternative explanations kept failing. And after 18 months of work, 18 months of simulations and calculations and arguments and revisions and more simulations, Batygin and Brown arrived at their conclusion. The simplest explanation for the clustering of extreme trans-Neptunian objects was a planet, a specific kind of planet with specific orbital properties in a specific region of the outer solar system. The mathematics was not ambiguous. Something is there. Now, how you find a planet you cannot see. The method Brown and Batygin used to infer. Planet 9's existence belongs to a proud tradition in the history of astronomy. In 1781, William Herschel discovered Uranus, the first planet found with a telescope, the first planet discovered in recorded history. As astronomers tracked Uranus over the following decades, something troubling became apparent. Uranus was not where it should be, and its actual position in the sky deviated from the position predicted by calculations based on the known gravitational influences of the Sun and the other planets. Something was pulling on Uranus, something unknown, something not yet discovered. In the 1840s, two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, working independently, used Newton's laws of gravitation to work backward from the anomalies in Uranus's orbit to the properties of the hypothetical perturbing body. On September 23, 1846, the German astronomer Johann Galle pointed his telescope at the position Le Verrier had calculated. Neptune was there, not approximately there, exactly there, within 1 degree of the predicted position. And this was one of the most spectacular confirmations of mathematical prediction in the history of science. Newton's mathematics, applied carefully to observed orbital anomalies, had predicted the existence and location of an entire world before anyone had ever seen it. Brown and Batygin were doing the same thing, working backward from orbital anomalies to the properties of the object causing them, using mathematics to trace the invisible gravitational hand shaping the edge of the solar system. The method worked for Neptune. The question was whether it would work for Planet 9. The simulation. The heart of Brown and Batygin's analysis was a computational simulation. They modelled the outer solar system, Neptune, the Kuiper belt, the extreme trans-Neptunian objects, and then added a hypothetical massive planet with various different orbital properties. For each set of planet properties, they ran the simulation forward in time, millions of years, to sometimes hundreds of millions of years, and watched what happened. How did the hypothetical planet affect the orbits of the smaller objects? Did its gravitational influence produce the clustering observed in the real data? The simulations were run thousands of times. Each run was a different hypothetical planet, different mass, different orbit, different distance. Finding the right set of parameters required systematically exploring that space, running simulations. Comparing results to observations, refining the estimates. What emerged after months of this process was a remarkably specific picture. The planet had to be massive, at least 5 times Earth's mass, probably more. Too small and it could not produce the observed clustering. Too large, much larger than 10 Earth masses, and it would disrupt the entire outer solar system in ways not observed. The planet had to be in a highly elongated orbit, and a circular orbit at any distance did not produce the right clustering pattern. The elongation was essential. The planet's orbit had to be roughly anti-aligned with the cluster of extreme trans-Neptunian object orbits. In other words, the extreme trans-Neptunian objects cluster in one direction, and Planet 9's elongated orbit points in the opposite direction. And the planet had to be inclined to the ecliptic, tilted relative to the plane in which the other planets orbit, by roughly 6 degrees. Every one of these properties is a specific testable prediction. The planet is not just something big somewhere out there. It is a world with defined characteristics, orbiting in a defined region of space. Find an object with those characteristics, and you have found Planet 9. January 20th, 2016. The press conference at Caltech was crowded, and science journalists from around the world had gathered. Not because they knew exactly what was being announced, but because the word had gotten out that it was something significant. Brown stood at the podium and said the words that would be quoted in newspapers and websites and science blogs for years afterward. He said, "We have found strong evidence that there is a 9th planet in our solar system." The room went quiet for a moment. Then the questions began. And is this the same as the Planet X that people have been talking about for 100 years? No, Brown said. Planet X was a hypothetical planet invoked to explain anomalies in the orbits of Uranus and Neptune, anomalies that turned out to be measurement errors. Planet 9 is something different. It is predicted by real, specific orbital anomalies in real, recently discovered objects. Have you actually seen it? Oh, Brown said. We have not seen it. We have predicted it. Yeah, the mathematics tells us it should be there. Now we have to find it. How confident are you? Very confident, Brown said. He estimated the probability that the clustering of the extreme trans-Neptunian objects was a statistical fluke at roughly 1 in 10,000. The scientific community's reaction was mixed, as it always is when a significant claim is made without direct observational confirmation. Some astronomers were immediately intrigued, others were skeptical. The debate that began that day in January 2016 has not ended. It has deepened and broadened and grown more sophisticated as more data is accumulated. But the core claim that something massive and distant is shaping the orbits of extreme trans-Neptunian objects has not been convincingly refuted. The math still points towards something. What Planet 9 actually is. Let us set aside for a moment the question of whether Planet 9 exists. Let us assume it does. And let us take the mathematics at face value and ask, what kind of world is this? A super-Earth, or more precisely a mini-Neptune, a planet in the mass range between 1 and 10 times Earth's mass, a class of planet that is, it turns out, the most common type in the galaxy. Surveys of exoplanets have found that planets in this size range are extraordinarily abundant. Nearly every star in the sky is likely to have at least one planet in this mass range. Our solar system, oddly, has none. The Mercury, Venus, Earth, Mars, but the rocky planets are all less than 1 Earth mass. Jupiter, Saturn, Uranus, Neptune, the giants, are all much larger. There is a conspicuous gap in our solar system's planetary population between 1 Earth mass and 15 Earth masses, the very mass range that seems to be the most common in the galaxy. Planet 9, if it exists, would fill that gap. It would be, in a sense, the missing member of our solar system's family. Ice and darkness. At the distances Planet 9 is predicted to inhabit, the temperature is extraordinarily low, approximately negative 220 degrees Celsius. To put that in perspective, the coldest temperature ever recorded on Earth's surface was negative 89 degrees Celsius. Planet 9's surface temperature is more than twice as cold as the coldest place on Earth. At that temperature, most gases would be partially or wholly frozen. And even carbon dioxide would be frozen at Planet 9's temperatures. Planet 9's atmosphere, if it has one, would be extraordinarily thin. Most of what might have been its atmospheric gases would have frozen onto its surface over the billions of years it has spent in the outer darkness. What would it look like? Almost certainly dark. Very dark. Without significant sunlight to heat its surface, without active geology to resurface it, thus Planet 9 would likely have accumulated a coating of ancient, darkened organic compounds, the products of billions of years of cosmic ray bombardment on its surface ice. Astronomers call this material tholin. In the darkness, covered in ancient organic material, orbiting in its vast ellipse over tens of thousands of years, patient, invisible, waiting the revised estimates. Science is not static. the most recent analyses, incorporating data from the 51 object study published in 2024 and additional modelling work published in 2025, suggest mass approximately 5 Earth masses, distance approximately 290 to 500 astronomical units, closer and somewhat less massive than originally thought. Closer is better for detection. A planet at 300 astronomical units is significantly brighter than one at 700 astronomical units, in a large area of sky. The Rubin Observatory has been searching for Planet 9 for years, but it is still extraordinarily faint, still extraordinarily distant, still hiding in a large area of sky. The Rubin Observatory is looking, and August 20 to 26 is coming. A history written in the chaos. To understand Planet 9, where it came from, why it is where it is, why it moves the way it moves, you need to understand something about the early solar system. It was not peaceful. Though the picture most of us carry in our minds of the solar system's formation is a gentle one, a cloud of gas and dust slowly condensing, planets quietly assembling from the available material, everything settling into orderly orbits over millions of years, like sand settling to the bottom of a still pond. This picture is wrong. The early solar system was not a still pond. It was a storm, a 4 billion-year-old catastrophe that left scars we can still read in the craters of the Moon, and in the strange tilts of Uranus and Venus, in the peculiar architecture of the asteroid belt, and perhaps in the existence of a hidden planet at the edge of everything. The violence began almost immediately. In the first 100 million years of the solar system's history, a period called the Late Heavy Bombardment, the inner planets were struck by an extraordinary number of large impactors. The Moon's cratered surface is the most visible record of this bombardment, as some of those craters are hundreds of kilometers across, formed by impacts so energetic they would have temporarily vaporized entire regions of a planet's surface. But the bombardment was not random. It was caused. Something had disturbed the asteroid belt and the Kuiper belt, flinging objects out of their stable orbits and sending them careening toward the inner solar system. The something was the giant planets, Jupiter and Saturn specifically, the nice model. In 2005, a team of planetary scientists published a series of papers that fundamentally changed our understanding of the solar system's history. The model was developed primarily at the Observatoire de la Côte d'Azur in Nice, France. It is called simply the NICE model. The NICE model begins with the giant planets, Jupiter, Saturn, Uranus and Neptune, in orbits much more compact than their current ones. All 4 giant planets were initially much closer to the Sun than they are today. That they were packed together, orbiting in a relatively small region of the outer solar system, while beyond them lay a vast disk of icy planetesimals. For perhaps the first 500 million years of the solar system's history, this configuration was stable, and then Jupiter and Saturn crossed a critical threshold. As Jupiter and Saturn's orbits slowly evolved, they reached a point where their orbital periods were in a specific ratio, 1 to 2. For every one orbit Saturn completed, though Jupiter completed exactly 2. This kind of orbital relationship is called a resonance, and resonances have dramatic consequences in gravitational systems. The resonance destabilized everything. Jupiter and Saturn were flung outward. Their orbits expanded dramatically. The expansion sent gravitational shockwaves through the entire outer solar system. Uranus and Neptune were scattered. Some models suggest Neptune was actually closer to the Sun than Uranus initially. And the 2 planets switched positions during the upheaval. The icy disk beyond the giant planets was catastrophically disrupted. Billions of icy objects were flung in all directions, inward toward the inner solar system, producing the Late Heavy Bombardment, and outwards toward the vast distances of the outer solar system and beyond. This is where the Oort cloud came from. This is where the Kuiper belt got its current structure. And this, some researchers believe, again is where Planet 9 came from. How Planet 9 got lost. If Planet 9 exists, how did it end up in such an unusual orbit, at such enormous distances? The most widely discussed explanation involves exactly the kind of planetary upheaval described by the NICE model. In the early solar system, there may have been not 4 giant planets, but 5. Computer simulations of solar system formation have shown that it is quite common for more planets to form than survive. The gravitational interactions between multiple giant planets during the early chaotic period of solar system history can be violent. Planets are scattered into new orbits, sometimes ejected from the solar system entirely. Planet 9 may be a survivor of exactly this kind of scattering event. The scenario works like this. In the early solar system, a fifth giant planet, or a super-Earth, yet in the mass range now predicted for Planet 9, formed in the region between the current orbits of the outer planets. During the NICE model upheaval, this additional planet interacted gravitationally with Jupiter. Jupiter's kick sent it into a highly elongated orbit, but not all the way out. Some planets, in similar scenarios, are ejected completely, sent on hyperbolic trajectories that escape the solar system entirely, becoming rogue planets drifting through interstellar space. So Planet 9, the theory goes, was not quite ejected. Jupiter's kick was strong enough to send it to enormous distances, but not quite strong enough to give it escape velocity from the Sun's gravity. There it has sat, for 4 billion years, following its vast elliptical path, alone in the dark, the rogue planet connection. There is a connection here that listeners of Science for Sleep may find particularly interesting. The rogue planets, planets that have been ejected from their home solar systems and drift freely through interstellar space, are the subject of one of the channel's previous journeys. And Planet 9, in the most widely accepted formation theory, came very close to becoming one. The difference between a rogue planet and a Planet 9 is the difference between a near miss and a full ejection. Jupiter's kick was strong enough to send the protoplanet 9 to enormous distances, but not quite strong enough to give it escape velocity from the Sun's gravity. Had Jupiter's kick been 10% stronger, Planet 9 would not be hiding at the edge of our solar system. It would be drifting between the stars, a cold, dark, lonely world with no sun, invisible to us, unknown. Instead, it remains bound to our system by a thinnest gravitational thread. That this near-miss quality is a part of what makes Planet 9 so scientifically fascinating. It is potentially a planet on the boundary between belonging and not belonging, between gravitationally bound and free, a world that the solar system almost lost 10,000 years. Let us think about what an orbital period of 10,000 to 20,000 years actually means. 10,000 years ago, the last glaciers of the most recent ice age were retreating. Rather, the Sahara Desert was green, a savanna full of lakes and wildlife. Humans were just beginning to plant crops and domesticate animals. The concept of writing would not be invented for another 5,000 years. 20,000 years ago, the ice sheets of the last glacial maximum covered much of northern Europe and North America. Mammoths walked the tundra. In the time between then and now, all of human civilization has risen and fallen and risen again. Agriculture, cities, empires. So religions, sciences, arts, technologies, all of it has happened in less than one orbit of Planet 9. Planet 9 completes one orbit while we build and lose everything. This is the time scale on which the outer solar system operates. For Planet 9, human history is barely a moment. The entire span of recorded civilization is a small fraction of one trip around the Sun. So the gravitational shepherd, one of the most important concepts in understanding Planet 9's influence on the outer solar system, is the idea of secular resonance. Over millions of years, Planet 9's gravity slowly shepherds the extreme trans-Neptunian objects. It pushes their orbits into configurations that are stable relative to Planet 9's own orbit. It confines them, herds them, organizes them. The clustering we observe, the reason Brown and Batygin became suspicious in the first place, is the direct result of this shepherding. Planet 9 is a gravitational shepherd, and the extreme trans-Neptunian objects are its reluctant flock. The inclined orbit and its consequences. Planet 9's orbit is predicted to be inclined roughly 6 degrees to the ecliptic. 6 degrees sounds small, but in the context of the solar system's architecture it is significant. So the 8 known planets all orbit within a few degrees of the ecliptic. A planet inclined 6 degrees to that plane would spend most of its time above or below the ecliptic in regions of sky that traditional planet searchers have not systematically surveyed. This explains, in part, why Planet 9 has not been found despite decades of outer solar system surveys. But the inclined orbit has a more important consequence than just making Planet 9 harder to find. And if Planet 9 exists in an inclined orbit, it should leave specific signatures in the orbits of extreme trans-Neptunian objects. Not just in the clustering of their perihelion directions, but in the distribution of their orbital inclinations. This prediction has been tested. The inclination distribution of the known extreme trans-Neptunian objects is consistent with the Planet 9 hypothesis. Another piece of the puzzle fitting into place. To the orbit visualized, let us try to visualize Planet 9's orbit, not mathematically, intuitively, as a physical thing moving through space. From above the ecliptic plane, the 8 known planets trace nearly circular paths around the Sun. Now add Planet 9. Its orbit would look wildly different from the others. It is enormously elongated, an ellipse so stretched that it barely looks like a circle at all. At one end, close to the Sun, as the orbit dips to its perihelion, perhaps 250 astronomical units. At the other end, it stretches to its aphelion, perhaps 700 or 800 astronomical units. And Planet 9 itself, a dark, cold, massive world, moves along this orbit so slowly that in 10,000 years it would complete only one full circuit. In a human lifetime, it would move a fraction of a degree along its path, patient and steady to dark. Voyager 1, the most distant human-made object, has been travelling for nearly 50 years at speeds no rocket has ever matched, and it is only about 160 astronomical units from the Sun. Planet 9 at its closest approach is nearly twice as far. The distances involved are not just large, they are almost impossible to grasp intuitively, and somewhere in that vast darkness, if the mathematics is right, a world is moving, slowly, steadily, waiting to be found. 51 objects, the scientific case for Planet 9 rests, at its foundation, on the orbital behaviour of a specific population of objects at the edge of the solar system. And that case has grown considerably stronger since 2016. In 2024, a team of researchers published the most comprehensive analysis of the Planet 9 hypothesis to date. They examined the orbits of 51 extreme trans-Neptunian objects and asked whether their orbital properties were consistent with the Planet 9 hypothesis. The answer was yes, not unambiguously yes. And not yes beyond any doubt yes, but yes in the way that careful science works, consistent with the hypothesis, statistically significant even after accounting for observational biases, supporting the conclusion that a massive distant perturber is the most likely explanation for the observed orbital clustering. The clustering, what it actually shows. The clustering of extreme trans-Neptunian object orbits involves multiple orbital parameters, each of which contributes a piece of the evidence. At the first is the argument of perihelion, the direction in three-dimensional space that each object's elongated orbit points. For a population of objects distributed randomly around the solar system, the arguments of perihelion should be spread evenly across all directions. Instead, the known extreme trans-Neptunian objects show a preference for certain directions. The second is the longitude of ascending node, related to the orientation of each object's orbit in space. Again, so random distribution would give an even spread. The observed distribution is not even. The third, and perhaps most striking, is what researchers call the physical clustering, the fact that the actual perihelion positions of the extreme trans-Neptunian objects are concentrated in one region of space. Each of these clustering signals, taken alone, might be dismissed as statistical noise. Together, that they paint a coherent picture of a gravitational influence organising the outer solar system from afar. The predictions that came true. A scientific hypothesis is only as good as its predictions. The history of science is full of hypotheses that explained known facts perfectly, but failed when asked to predict new ones. Planet 9 has made several specific predictions, and several of those predictions have subsequently been confirmed. At the first and most dramatic is the prediction of highly inclined orbits. When Brown and Batygin published their 2016 paper, they noted that their simulations produced a population of objects in highly inclined orbits, inclinations of 90 degrees or more. At the time, such objects were not known in the relevant part of the solar system. They were subsequently discovered. The second confirmed prediction involves a specific type of orbit called an L-shaped orbit, an orbit where the object's perihelion is oriented roughly perpendicular to the plane of the solar system. Such objects have been found. The third involves the Sedna-like detached objects. Planet 9's gravity naturally produces such objects in simulations. The discovery of new Sedna-like objects has continued to confirm this prediction. Each confirmed prediction is a point in Planet 9's favour. That the score so far is running in Planet 9's favour. Science requires skepticism. Let us be honest about something. The evidence for Planet 9 is compelling, the mathematics is sophisticated. The predictions have come true. The statistical case, while debated, is significant. But Planet 9 has not been found. And until it is found, until a telescope captures its light and an orbit is calculated and the world is confirmed, the hypothesis remains unconfirmed. As science demands that we hold this distinction clearly, compelling evidence is not proof, a well-confirmed prediction is not a discovery. The skeptics of Planet 9 are not wrong to be skeptical, they are doing their job. The selection effect argument. The most persistent and most technically serious objection to the Planet 9 hypothesis involves selection effects. Here is the core of the argument. The extreme trans-Neptunian objects used to infer Planet 9's existence were not found by a systematic, unbiased, all-sky survey. They were found by various research groups using various telescopes searching various parts of the sky at various times. If the searches were concentrated in certain regions of sky, and if those regions happened to lie in the direction where the extreme trans-Neptunian object perihelia appear to cluster, and then the clustering could be an artifact of where astronomers looked rather than a real feature of the outer solar system. This is a legitimate concern, it cannot be dismissed. The response from Planet 9 proponents is that they have carefully modelled the selection effects and found that even after correcting for these biases, a significant clustering signal remains. The response from skeptics is that the selection effect modelling is imperfect and uncertain, and that a null result, no planet, is still entirely consistent with the data. Both sides are right about something. The question is how much of the signal the selection effects explain. The Rubin Observatory, with its systematic and unbiased all-sky survey, will provide the cleanest possible test of this debate. Jean-Luc Margot and the critics. One of the most prominent skeptical voices in the Planet 9 debate belongs to Jean-Luc Margot, a planetary scientist at UCLA. Margot has published analyses arguing that the statistical case for Planet 9 is weaker than Brown and Batygin claim, that the clustering signal, when properly corrected for selection effects, is not statistically significant. Brown and Batygin have responded to Margot's analyses in detail, pointing to what they see as methodological choices in his work that they believe underestimate the clustering signal. The exchange between these groups is technical, detailed, and ongoing. And it is exactly how science should work. The argument will not be resolved by debate, it will be resolved by data. What non-detection would mean? If the Rubin Observatory completes its survey and Planet 9 is not found, what would that mean? First, it would not necessarily mean Planet 9 does not exist. Rubin's survey is deep but not infinite. If Planet 9 is at the far end of its orbit, approaching aphelion, at 800 or more astronomical units from the Sun, it might be too faint for even Rubin to detect. But if Planet 9 is in the more favourable part of its orbit, within 400 or 500 astronomical units of the Sun, Rubin should find it. A non-detection at those distances would be a serious blow to the hypothesis. If Planet 9 is not found where the mathematics predicts it should be, one of several things must be true. The clustering is a statistical artifact, or Planet 9 exists but is currently beyond Rubin's reach, or the clustering is real but caused by something other than a single massive planet. Each of these outcomes would be scientifically significant. Science would move forward, it always does, but the discovery, if it comes, would be more dramatic by far. The haystack. Finding Planet 9 has been compared by astronomers who study the outer solar system to finding a specific needle in a very large haystack. The comparison is apt, but it understates the scale of the problem. The haystack is the sky. The relevant portion of the sky covers hundreds of square degrees. Each square degree of sky, observed to the depth required to detect a faint distant planet, contains tens of thousands of individual objects. Stars, galaxies, asteroids, Kuiper belt objects, distant quasars. Planet 9, if it exists, is one of those objects, indistinguishable in any single image from thousands of others. The only thing that distinguishes it is its motion, its slow drift across the sky over months and years. To find Planet 9, you must take multiple images of the same region of sky, separated by days or weeks or months, and identify the objects that have moved. Then, among all the objects that have moved, identify the specific object moving at the rate expected for a planet at 500 astronomical units. This is straightforward in principle. In practice, it requires enormous amounts of telescope time, is sophisticated image processing software, and patience measured in years. The Subaru Search. The most systematic dedicated search for Planet 9 has been conducted using the Hypersuprime Cam on the Subaru telescope in Hawaii. The Hypersuprime Cam can image an area of sky 8 times the size of the full moon in a single exposure. At Subaru's aperture of 8.2 meters, this wide-field camera can reach objects far fainter than anything typical survey telescopes can detect. The Brown's team has used Subaru to conduct targeted searches of the regions of sky where Planet 9 is most likely to be found, the arc extending from Orion through Taurus and Gemini. The searches have been deep. They have reached the faintness levels where Planet 9 should be detectable at the closer end of its predicted distance range, and the crew have found many things: asteroids, Kuiper belt objects, a rich population of outer solar system bodies, but not Planet 9. This does not mean it is not there. The total area search covers only a fraction of the possible position space, and if Planet 9 is near the far end of its orbit at 700 or 800 astronomical units, it would be too faint for even Subaru to detect. The search continues, but the real hope now rests with Rubin. The Vera C. Rubin Observatory. The Vera C. Rubin Observatory is named after Vera Rubin, the astronomer whose careful measurements of galaxy rotation curves provided some of the strongest early evidence for the existence of dark matter. She died in 2016, the same year Brown and Batygin announced their Planet 9 evidence. The observatory sits at an altitude of 2,700 meters in the Chilean Andes. Its telescope has an 8.4-meter primary mirror. Its camera, the Legacy Survey of Space and Time camera, has 3 billion pixels, and making it the largest digital camera ever built for astronomical use. Every clear night, the Rubin Observatory operates automatically, scanning the sky according to a predetermined schedule. Over its 10-year primary mission, it will image the entire visible southern sky approximately 800 times. In this map, if Planet 9 exists, if the mathematics is right, if the clustering is real, if something massive is indeed hiding in the darkness beyond Neptune, Planet 9 should appear. An old data, new eyes. There is a theme that runs through the history of outer solar system astronomy, and it is the same theme that runs through the Venus story Science for Sleep told not long ago. Old data contains discoveries that nobody has yet made. 2 infrared space telescopes, IRAS, which operated in 1983, and Akari, which operated from 2006 to 2011, surveyed the entire sky in infrared light. Both produced enormous datasets of infrared sources. In 2021, and a team of researchers, Mike Brown among them, reported a possible Planet 9 candidate in the combined IRAS and Akari data. The object appeared in one dataset, but not definitively in the other. Its tentative position in the constellation Eridanus was consistent with some versions of the Planet 9 orbital prediction. The result was not definitive, but the hint exists. It is being followed up. The region of Eridanus is being searched. The 2025 updates. In early 2025, the Rubin Observatory began its first full year of systematic sky survey operations. The data pipeline began accumulating observations. Outer solar system researchers began receiving the first alerts, notifications of new moving objects detected by the automated software. Among those alerts were several new extreme trans-Neptunian objects. The 2025 discoveries, as they have been incorporated into analyses, have continued to support the clustering. But no new objects have been found in orientations that significantly contradict the Planet 9 prediction. Simultaneously, the theoretical work has continued. The most comprehensive 2025 analysis places Planet 9's mass at approximately 5 Earth masses, and its current position at a distance of 200 to 400 astronomical units, significantly closer than some earlier estimates. Closer means brighter. Brighter means easier to detect. Brown's confidence, as expressed in recent interviews, remains high. He has described the current state of the Planet 9 search as the most exciting it has ever been. Where Planet 9 is now. Based on the current best estimates, researchers have identified a region of sky where Planet 9 is most likely to be at the present time. The most probable current location is in the direction of the constellations Orion and Taurus, specifically an arc extending roughly from the position of the Orion constellation toward the Gemini-Taurus border. This is a region of sky accessible from the Rubin Observatory's position in Chile. It is being surveyed. The data is accumulating. If Planet 9 is in this region, and if it is within the closer end of the predicted distance range, 2 to 400 astronomical units, then it should appear in the Rubin data within the next year. Brown has been specific about his timeline, that he expects that by the time the Rubin Observatory has completed its first 2 years of full operations, approximately August 2026, there will be an answer. The telescope is running, the data is flowing, the algorithms are searching. Somewhere in the Orion direction of the sky, at a distance of perhaps 300 astronomical units, a darker and frozen world may be moving. Slowly, patiently, in its vast orbit that takes 10,000 years to complete, waiting to be found. Checo, the greatest discovery in a century. Let us set aside the uncertainty for a moment and follow the hypothesis to its conclusion. Planet 9 is real. It exists. The Rubin Observatory finds it. A faint, slow-moving point of light in the direction of Orion, confirmed by follow-up observations, with an orbit that matches the prediction exactly. What happens next? The last planet discovered in our solar system, Neptune, was found in 1846, 175 years ago. And in that time, human civilization has transformed beyond recognition. We have invented radio, television, computers, the internet, nuclear power, genetic engineering, space travel. We have photographed every planet in the solar system. We have landed on the moon and sent robots to Mars. And in all that time, we have not discovered a new planet. Not one. A confirmed Planet 9 would end that drought. It would be the first new planet discovered in 175 years. The magnitude of that is not just scientific, it is cultural. It changes the solar system we grew up learning about. It adds a chapter to the story of where we live. Planet 9 as the solar system's missing link. From a purely scientific standpoint, the discovery of Planet 9 would be significant for reasons beyond the simple fact of a new planet. It would solve a specific and long-standing puzzle in planetary science, our solar system. It, compared to the exoplanet census of other star systems, has a glaring gap. The most common type of planet in the galaxy, the super-Earth or mini-Neptune, with a mass between 1 and 10 times Earth, but is absent from our solar system. We have rocky planets smaller than Earth and gas giants much larger, but nothing in between. Planet 9, with its predicted mass of approximately 5 Earth masses, would fill the gap, and its discovery would tell us that the gap is not real, that our solar system does have a planet in the super-Earth mass range, just not where we expected it to be. Stranded in the outer darkness instead of orbiting at a comfortable distance from the Sun, this would have profound implications for theories of planet formation. Planet 9 and the exoplanet connection. The study of exoplanets has revealed that the universe is full of worlds. Planets are not rare special objects, though they are a nearly universal feature of star systems. Almost every star has planets, and among all the planets that have been catalogued, the super-Earth and mini-Neptune mass range is far and away the most common. Our solar system, lacking any planet in this range, has often been described as unusual. If Planet 9 exists, that conclusion changes. Our solar system has a super-Earth, and it is just in a very unexpected place, stranded at the edge of the solar system by the chaos of the early solar system's history. This reframes our solar system's position in the cosmic context. Not unusual, just structured differently. If Planet 9 is confirmed, the map of the solar system will be redrawn. Not just with a new dot added at the far edge, more fundamentally than that. The discovery will require a revision of our understanding of the solar system's architecture and history. Current models of the solar system, models that have been refined over decades, were built without Planet 9. They did not need to account for a massive distant planet because no such planet was known. With Planet 9 confirmed, all of those models would need to be revised. The influence of a 5 Earth mass planet on the outer solar system is significant. And of long-period comets arriving in the Oort cloud would look different in models that include Planet 9. The rate and distribution of long-period comets arriving in the inner solar system might be shaped in part by Planet 9's gravity. This could affect our understanding of the cometary bombardment history of Earth, and therefore the history of the delivery of water and organic molecules to the early Earth. Though these are not small revisions, they are fundamental changes to our picture of where we live and how our home came to be what it is. Geothermal heat. Could Planet 9 support life? This question is speculative and must be prefaced with strong caveats, but it is a question that planetary scientists genuinely ask. At 400 to 800 astronomical units from the Sun, Planet 9 receives essentially no solar energy. The surface is predicted to be at roughly negative 220 degrees Celsius, far too cold for any chemistry we associate with life. But surface temperature is not the whole story. Planets generate heat internally. The Earth's interior is hot enough to produce volcanic eruptions. This internal heat comes from two sources: the residual heat of the planet's formation and the ongoing heat produced by the radioactive decay of elements within the planet's interior. A planet 5 times Earth's mass would have substantially more internal heat than Earth. That heat would flow upward through the planet's interior, warming the rock and any liquid water or ice that might exist at depth. Could there be liquid water inside Planet 9? Beneath its frozen surface warmed by its internal heat? The answer is possibly. Europa, one of Jupiter's moons, has a liquid water ocean beneath its ice shell, maintained by tidal heating rather than solar energy. But this is not a prediction. It is a possibility, a speculation. But it is a speculation based on real physics. The universe is more creative about where it puts potentially habitable environments than we initially expected. Europa, Enceladus, Titan, the subsurface of Mars, and perhaps, in the deepest speculation, the interior of a frozen world at the very edge of our solar system. To naming the planet. There is a question that nobody talks about much in the scientific literature, but that everyone quietly thinks about. What would Planet 9 be called? The 8 known planets are named after Roman deities: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The tradition stretches back to antiquity. A new planet would need a new name. The International Astronomical Union would have to approve it. The discoverers would propose a name. Brown, in interviews, has declined to propose a specific name before the planet is confirmed. He has said only that it would need to be a name worthy of the planet, something significant, something that captures the mystery and the darkness and the long wait. The god of the underworld is already taken. That is Pluto's domain, in a delicious irony. Perhaps a deity of darkness, of the deep cold, of the outer darkness beyond the light of the sun. The names will be proposed and debated and decided in due course. And if the planet is found, a tradition of ghosts. Planet 9 is not the first hidden planet to haunt the edges of the solar system. The history of astronomy is threaded with phantom planets. Worlds predicted from mathematical anomalies, searched for with great dedication, and found or not found in ways that illuminate how science works at its frontier. The most famous success of this method is Neptune. In 1781, William Herschel discovered Uranus. As astronomers tracked Uranus over the following decades, something troubling became apparent. Uranus was not where it should be. Its actual position in the sky deviated from the position predicted by calculations. Something was pulling on Uranus, something unknown. Adams and Leverrier used Newton's laws to predict Neptune's location. Galley pointed his telescope. Neptune was there, but the Neptune story has a complication less often told. After Neptune was found, astronomers continued to track Uranus, and they found, or thought they found, that the anomalies in Uranus's orbit were not fully explained by Neptune. There was a residual. Something else was needed. Percival Lowell devoted enormous resources to searching for Planet X from his observatory in Flagstaff, Arizona. Lowell died in 1916 without finding it. In 1930, a young astronomer named Clyde Tombaugh found something. A faint, slow-moving object in the outer solar system. It was Pluto. Pluto was initially hailed as the discovery of Lowell's Planet X, but it quickly became apparent that Pluto was far too small to have caused the anomalies in Uranus's orbit. When Voyager 2 flew past Neptune in 1989 and provided an accurate measurement of Neptune's mass, astronomers could recalculate Neptune's gravitational influence on Uranus. The revised calculations showed that Neptune, with its corrected mass, completely explained the observed anomalies. There were no residual anomalies. There was no Planet X. The residual anomalies that had driven 60 years of searching had been caused by measurement errors in Neptune's mass. The lesson: apparent orbital anomalies can arise from measurement errors, not just from unseen planets. Brown and Batygin are aware of this history. They take it seriously. Their analyses have been designed to avoid the specific pitfalls of the Planet X era. The scientists behind the search. Mike Brown grew up in Huntsville, at Alabama, the city where the Saturn V rockets that carried humans to the moon were built. Space was in the air. He studied physics as an undergraduate and then pursued astronomy for graduate school, eventually landing at Caltech. His work focused on the outer solar system, Kuiper belt objects, trans-Neptunian objects, the icy population at the edge of the solar system. Brown is not a typical academic scientist. He wrote a popular book on how I killed Pluto and why it had it coming, it appeared. That became a bestseller. He's willing to engage publicly with his work in ways that most researchers avoid. He is also, by his own account, possessed of a competitive streak that has served him well in a field where discoveries require patience and persistence. In a 2024 interview, he described the current state of the search in characteristic terms. The evidence has only gotten stronger, he said. The Rubin Observatory is a game changer. If the planet is where the math says it should be, we will find it within 2 years. 2 years from 2024 is 2026, the date he named, August 1st. The theorist, Konstantin Batygin, is a different kind of scientist than Brown. Where Brown is primarily an observational astronomer, Batygin is a theorist. His tools are equations and computers. His domain is the mathematics of orbital dynamics and the long-term behavior of gravitational systems. Batygin was born in Russia and spent part of his childhood in Japan before his family moved to the United States. He joined Caltech's faculty, where he has built a reputation for work that is mathematically sophisticated and physically intuitive in equal measure. He plays guitar, he has a band. He does not look like the stereotype of a quiet, introverted mathematician. He is energetic and unconventional and genuinely delighted by the mathematics of planetary motion. When Brown brought him the clustering problem in 2014, Batygin was 30. The 18 months of work that followed resulted in what both men describe as a genuine partnership, not a senior scientist directing a junior one, but two researchers with complementary skills working toward a shared goal. Batygin has said in interviews that the Planet 9 problem is the most interesting problem he has ever worked on. Not because of the celebrity of the potential discovery, but because of the mathematical richness of the problem. The dynamics of the outer solar system with a distant massive perturber are genuinely complex and genuinely beautiful. He continues to refine the theoretical models. Each new discovery of an extreme trans-Neptunian object is new data to incorporate. Each new analysis is a test of the theory. The mathematics is converging. The answer is approaching. Or the broader community. Brown and Batygin are the most visible faces of the Planet 9 hypothesis, but the search involves a much larger community. At observatories around the world, in Chile, in Hawaii, in the Canary Islands, in Australia, researchers are conducting surveys of the outer solar system. Some are specifically looking for Planet 9. Others are pursuing different scientific goals and finding extreme trans-Neptunian objects as a byproduct. And each discovery feeds into the database. Each new orbit is another data point. The community grows, the dataset grows, the statistical power of the analysis grows. Simultaneously, theorists are working on the dynamics, refining the orbital models, testing alternative explanations, running simulations with updated parameters. And the skeptics continue to probe and challenge the interpretation, looking for alternative explanations, questioning the statistical methods, are pressing for more rigorous accounting of selection effects. This is science, messy, contentious, slow, self-correcting, moving toward the truth not in straight lines but in spirals. The Planet 5. Hypothesis. Some versions of the NICE model include a fifth giant planet, sometimes called Planet 5 in the literature. In these models, the early solar system had not 4 but 5 giant planets, and the gravitational interactions of the early chaotic period caused one of them to be ejected from the solar system. Computer simulations of solar system formation have shown that models with 5 initial giant planets often produce outcomes that match the current solar system better than models with only 4. The 5th planet gets ejected. Jupiter's gravity kicks it out. It becomes a rogue planet, drifting through interstellar space. And here is the connection. It gets kicked into a very distant orbit without quite escaping. It becomes Planet 9. The Planet 5 and Planet 9 stories may be the same story. If Planet 9 is found, its properties, its mass, its orbit, its composition, will help determine which story is correct. These distinctions can be measured. After the discovery, the science will not end, it will intensify. The instruments of discovery, finding Planet 9 requires specific capabilities. Yet the planet is faint. because it is distant and receives little sunlight. It is slow-moving, because its orbital period is measured in thousands of years. It occupies a large area of sky, because the orbital constraints leave significant uncertainty in its position. The ideal telescope for finding Planet 9 needs 3 characteristics. It needs to be large, so it can collect enough light to detect a faint distant object. It needs to have a wide field of view, then so it can survey large areas of sky efficiently, and it needs to be operated in a way that allows the same regions of sky to be imaged multiple times, so that the slow motion of the planet can be detected. The Dark Energy Survey. The Dark Energy Survey operated from 2013 to 2019. It was designed to study the large-scale structure of the universe and the properties of dark energy, the mysterious force driving the accelerating expansion of the cosmos. The dark energy and Planet 9 are not obviously related topics, but the DES covered a large area of sky in the southern hemisphere to a considerable depth, and in that coverage, it found outer solar system objects, many of them, as a byproduct of its primary science mission. The Ammonite 2023 of KQ-14 was found using DES data. DES did not find Planet 9 itself. Its coverage did not include the region of sky where Planet 9 is currently predicted to be, but its contribution to the catalogue of extreme trans-Neptunian objects has been substantial. PanStar. The Panoramic Survey Telescope and Rapid Response System, PanSTARRS, is a facility at the Haleakala Observatory in Hawaii. Its repeated imaging of large areas of sky has revealed hundreds of Kuiper Belt objects and a smaller number of more distant bodies. PanSTARRS has searched for Planet 9 without success. Yet its coverage of the most likely Planet 9 region has been extensive but not deep enough to definitively rule out a planet at the predicted distance. The Detection Strategy. How will Rubin find Planet 9 if it is there? The detection strategy exploits Planet 9's motion. A planet at 500 astronomical units moves roughly 2 arcseconds per year, about 1/1000th of a degree. This is slow compared to nearby asteroids, but it is fast compared to background stars and galaxies, which do not move noticeably over the years of observation. The Rubin Observatory's software will analyze the accumulated images and identify all the objects that move from one epoch to the next. For each moving object, it will calculate a preliminary orbit and determine whether that orbit is consistent with a solar system object. Among the tens of millions of moving objects that Rubin is expected to find, one, if the Planet 9 hypothesis is correct, will have the specific motion and brightness consistent with a planet at the predicted distance. Brown's estimate that Planet 9, if it is at the accessible part of its orbit, will be found within a year or two of Rubin's full operation, is based on careful modelling of Rubin's capabilities against the predicted properties of Planet 9. August 2026, the date Brown named. That date is approaching. And after the announcement, let us follow the discovery through to its aftermath. Planet 9 is found. The Rubin Observatory detects a faint moving object in the direction of Orion. The automated orbit fitting software calculates a preliminary orbit. The object is at approximately 350 astronomical units, moving at the rate expected for a distant solar system body. Follow-up observations are triggered immediately. Other telescopes around the world point to the coordinates. Then Subaru confirms the detection. The orbit is refined, the orbital parameters match, the elongated elliptium, the appropriate inclination, the anti-alignment with the cluster of extreme trans-Neptunian objects. The paper is written, the peer review process, hastened by the significance of the result but not abbreviated, takes weeks rather than months. And then the announcement. It will be unlike any scientific announcement in recent memory. The discovery of a new planet in our solar system, the first in 175 years, would be major international news, not just for astronomy enthusiasts, but for everyone. The science that follows. The discovery of Planet 9 would immediately open a new chapter in solar system science. Not close a chapter, open one. The first question would be, what exactly is it? We would know its orbit. We would know its brightness, from which we could infer its size. So that we would know its position in the sky. What we would not know, not immediately, is its composition, its atmosphere, its internal structure, its surface features, its magnetic field, its moons. Getting those answers would require either very powerful spectroscopic observations from Earth-based or space-based telescopes, or, ultimately, a spacecraft mission. A spacecraft mission to Planet 9 would be a multi-generational project, at a distance of 300 to 500 astronomical units, and even the fastest spacecraft ever launched would take decades to arrive. Voyager 1, travelling at about 17 kilometers per second, would take more than 1,000 years to reach 500 astronomical units. A dedicated mission would require new propulsion technologies, perhaps solar sails, perhaps nuclear propulsion. It would require multi-decade mission timescales. It would require commitments from space agencies that extend beyond any individual scientist's career. None of this is impossible. But none of it is soon. The Kuiper Belt transformed. One immediate consequence of a confirmed Planet 9 would be a complete reanalysis of the Kuiper Belt. Current models of the Kuiper Belt have been built without Planet 9. They account for the gravitational influence of Neptune, but not for any more distant massive body. With Planet 9 confirmed, those models would need to be entirely rebuilt. The influence of a 5-Earth mass planet on the Kuiper Belt operating over billion of years would have left specific signatures in the Kuiper Belt structure. And some of those results might be surprising. They might reveal that Planet 9 has been involved in shaping the Earth's bombardment history, the history of cometary impacts that may have delivered water and organic molecules to the early Earth, contributing to the conditions necessary for life. Planet 9's reach may extend, hidden in ways not yet understood, all the way to the conditions that made life on Earth possible. The longest odds in astronomy. There is a bet of sorts running in the planetary science community, not a formal bet with money and contracts, an informal one made in the currency of professional reputation and scientific confidence. Mike Brown has made his position clear. He believes Planet 9 is real. He has staked his professional credibility on that belief, publicly or repeatedly, and in interviews and papers and conference talks. If Planet 9 is not found, if the Rubin Observatory surveys the relevant portion of sky and finds nothing, Brown will have been wrong in a very public way. He seems comfortable with that risk. He has said in various ways that science requires the willingness to be wrong, that making a strong claim and testing it, rather than remaining safely agnostic, is how knowledge advances. And on the other side are the skeptics who have argued that the statistical case is weaker than Brown and Batygin claim, that selection effects could explain the clustering, that the hypothesis is premature. They too will be shown to be right or wrong by the Rubin Observatory data. In either case, the science will advance. In either case, questions will be answered that have been open for nearly a decade. About what the universe is teaching us. Teaching us. Let us step back from the specific question of Planet 9 and think about what the search itself tells us. We are in an era of unprecedented astronomical capability. The instruments we have built, the Rubin Observatory, the James Webb Space Telescope, the Event Horizon Telescope, LIGO, are so sensitive, so precise, so capable that they are revealing things about the universe that were completely inaccessible to previous generations. The James Webb Space Telescope is observing galaxies that formed less than 300 million years after the Big Bang, looking back in time more than 13 billion years. LIGO has detected gravitational waves from black holes merging a billion light-years away, and the Rubin Observatory is searching for a dark, frozen world at the edge of our own solar system. The range of scales is vertiginous, from the edge of the observable universe to the edge of our solar system. In all of this, the most fundamental thing the universe is teaching us is how much remains to be discovered. The cosmic microwave background is full of anomalies that are not fully understood. The nature of dark matter remains unknown, despite decades of searching. The source of the excess antimatter is a mystery. And in our own solar system, the region of space we have been studying most intensively for the longest time, there may be a planet we have not yet found. That the universe is not running out of secrets. It is revealing them at the pace it chooses, to the instruments sensitive enough to detect them. We are becoming more sensitive. Year by year, instrument by instrument, discovery by discovery, the pace of revelation is increasing. The most important question in planetary science. Brown has described the Planet 9 question as the most important open question in planetary science. He may be right. If Planet 9 exists, and its discovery would reshape our understanding of the solar system's architecture, history, and place in the broader context of planetary systems. It would fill the conspicuous gap in our solar system's planetary population. It would reopen the question of whether the extreme outer solar system could harbour, in some form, conditions relevant to life. If Planet 9 does not exist, if the Rubin Observatory rules it out at the predicted distances, that too would be a profound result. It would mean our current models of the outer solar system are fundamentally incomplete. Either outcome is important. Either outcome advances the science. The answer is coming. Maybe in months, maybe in a year, maybe in 2 years, but it is coming. A planet in the dark. Right now, as you listen to this, somewhere in the outer solar system, at a distance of perhaps 300, perhaps 500 astronomical units from the Sun, there may be a planet, not a hypothetical planet, not a mathematical abstraction, a real world. A massive, frozen, ancient world wrapped in ice and dark organic material, drifting through the absolute cold of deep space in an orbit that takes 10,000 years to complete. If it is there, and the mathematics says it should be, it has been there for 4 billion years. 4 billion years of sense, 4 billion years of cold. 4 billion years of following the same vast elliptical path around a sun so distant it is merely the brightest star in the sky. In that time, life arose on Earth. Multicellular life evolved. Fish crawled onto land, dinosaurs rose and fell, mammals spread across the continents, primates descended from the trees. A particular species of primate developed language and tools and fire and mathematics. And with the same mathematics that predicted Neptune 175 years ago, that species began to suspect that a planet was hiding in the dark. The suspicion is now backed by data, by the orbits of 51 small icy worlds at the edge of the solar system, all pointing in the same direction, by the mathematical predictions that have been confirmed, one by one, by the refined estimates of a planet approximately 5 times Earth's mass, and at a distance of perhaps 300 astronomical units. The evidence is not conclusive, not yet, but it is compelling. And the telescope that can settle the question is running right now, every clear night, scanning the sky, what we know and what we don't. We know that the extreme trans-Neptunian objects, Sedna, Biden, the Ammonite, and dozens of others, have orbital properties that are difficult to explain with the standard model of the solar system. That we know that the Planet 9 hypothesis provides a coherent and specific explanation for the observed clustering. The hypothesis is mathematically rigorous and makes testable predictions. We know that several of those predictions have subsequently been confirmed. We know that the Rubin Observatory is operating and surveying the outer solar system with unprecedented depth and coverage. What we do not know is whether Planet 9 is actually there. We have not seen it. The science is clear about what constitutes evidence and what constitutes a confirmed finding, and we have the former but not the latter. The answer may come in 2026. It may come sooner. It may take longer, but it will come, the edge of everything. There is something almost meditative about the outer solar system, about the distances involved, about the timescales. At 300 astronomical units, the Sun is 300 times farther away than it is from Earth, and its light takes 41 hours to arrive. Its warmth is essentially zero, and yet even there, the Sun's gravity holds. Even at 300 times Earth's distance, our star's gravitational influence is strong enough to bind a planet, to keep it in orbit, to prevent it from drifting away into interstellar space. The solar system extends, in a real sense, much farther than most people imagine. We live inside something enormous, and at the outer edge of that enormous thing, yet in the cold and the dark and the silence, there may be a world we have not met yet. 4 billion years old, patient beyond any human conception of patience. Following its vast orbit through the darkness, we have built the mathematics to predict it. We have built the telescopes to find it. We are, for the first time in the history of our species, capable of answering the question. Is there a 9th planet? The answer is coming. Good night. The story of Planet 9 is not over. As it is in the middle chapter, it's the chapter where the evidence has accumulated and the tools are ready, but the discovery has not yet come. The chapter of informed anticipation, of waiting for confirmation that will change, in a profound and lasting way, how we understand our place in the cosmos, carry it with you into sleep. The solar system above you, the one you can see when the sky is clear and the stars are out, extends far beyond what is visible. Beyond Neptune, beyond the Kuiper belt, out into the cold outer dark. And in that dark, something may be moving, slowly, steadily, in its orbit of 10,000 years. We named the stars, we found the planets, we sent machines to the edge of the solar system, and now, with better tools than we have ever had, we are listening for one more world. The mathematics says it is there. The telescope is looking. The answer is coming. Sleep well. The universe is watching over you, all of it, even the parts we haven't found yet. And somewhere in the outer dark, a world that has never seen a human face, that has never been touched by a spacecraft, that has never been anything but alone and cold and patient, is waiting, quietly in the dark, and as it has been waiting for 4 billion years.